I recently announced that I'll be creating content focusing on various different subjects in computer science. And in this video, we'll be talking about data structures, specifically arrays. For those who don't know me, my name is Byron Jenkins, and I'm a senior software engineer and educator. So I have created a Google slide deck to help me present this content. And I already went through an introduction. Let's talk about why data structures is important. So in my 6 years of software engineering, what I've realized, if it's not evident throughout your studies in computer science and software engineering, all problems are not the same. So there's no one-size-fits-all solution to problems. And data structures offers a solution that vary in efficiency. So how we measure the efficiency in specific data structures is by the time complexity of the operation and the space complexity, meaning how much space does that structure take up or the solution takes up. If you're familiar with Big O, you may be familiar with time complexity and space complexity. Now, let's go over the agenda. So the plan is to go over the definition of arrays, dynamic arrays, array operations, how data is stored. In that section, I kind of want to show you how things are stored on a stack and heap. I think that will be like a great opportunity for you to like kind of visualize the data. And the next slide, I'll go over time complexity for the operations that I walk through. And the last, showing you a code example with various programming languages like Python, C, and Java. If I'm doing this in C, you must know that I obviously care about my content because I don't enjoy coding in C. Last time I did that was in college. But let's talk about what's an array. So an array is a linear fixed size collection of elements which are accessible by index. So on the left side, you'll see a graphical representation of an array. On the right side, there are bolded terms that you should pay attention to or keep in mind when talking about arrays. That will help you when trying to work through pseudocode or algorithms. Let's talk about the use cases. The use cases, a common use case I see for arrays, especially in coding problems on LeetCode and HackerRank. If those who don't know, HackerRank and LeetCode are websites where you take coding challenges. Some companies use those websites or source problems from that website. So string manipulation is common, caching, sorting and searching. There are efficient ways to sort and search through an ordered array. There are various different algorithms like quick sort, merge sort, bubble sort, ranging from, good or bad runtime. Well, not runtime, time complexities. But I won't go in depth talking about that. This array is obviously unordered. And the last use case is sequential storage. So let's talk about the terms. Linear is arranged in a sequential fashion, and fixed size means immutable. The size cannot be changed. So once you define this array, it cannot be changed. This is also known as a static array. Now, element is a unit of data. Each element, 14, 9, 10, 15, 21, and even NULL are elements in an array, and they have a corresponding position in the array, which are index, a numerical position of element and collection. So 14 is at position 0, 9 is at 1, 10 is at 2, and how you are able to access the element is by using this signature here. It will be the name of the array, sub, and what I mean by sub is the open and close brackets. So array sub 2 will give you 10. Now, one thing that I should call out is that for arrays, the first index starts at 0 and the last index is n-1. N is the number of elements. From here to here, it's the number of elements. If you look at capacity, capacity is the number of elements the array can store. But the number of used elements or defined elements, I guess you could say, because null, you could consider that as empty or no value. So size or length, sometimes some programming languages either use length or size. You can consider that synonymous, but that represents the number of used elements. So you see from here to here is the used elements, which represents the size. Number of it is 5. That's the number of size. So dynamic arrays are resizable collections. And I know in the last slide, I said that arrays can't be resized, but dynamic arrays is where the collections can be resized. And common cases where you'll see that at is when the capacity is not known in advance. or the capacity may change dynamically during the runtime of the program. So there are operations that you should pay attention to, like insertion and deletion. I have some graphics here that shows the beginning result. So this is the beginning result and the end result when we insert 17 in the array. So when we insert 17, for this case, we see the size is 4 and the capacity is 4. The array is at capacity, and for insertion, what we do is we resize the array when the size or length meets capacity. So if you see here, we have 4 and here we have 8. So the capacity is doubled. The elements are shifted, and 17, the desired element, is inserted at the index. That's the end result. And of course, the size of the array is increased because we just inserted a new element. But I'm going to show the step-by-step process in the next slide. For deletion, we don't resize. We do not resize because in that specific index, the element inside of the array, we simply just set it to null. Null or any value that represent empty. You see right here is null at the end. We want to remove 15, but what actually happens is that we set the element to null and we shift the element so that the null value is at the end of the array. Now, just want to call out that programming languages typically don't shrink arrays when elements are removed. Instead, allocated memory for the dynamic array remains unchanged and may use a mechanism like setting elements to null or any value that indicates that it's null. Now let's talk about the first operation, which is access. And I talked about that in the beginning when I mentioned how you can access an element. So with the provided index, most programming languages allow you to retrieve the element in this fashion. As I mentioned before, the name of the array, sub index. We're going to stop using array, hopefully, in the slides because it's a terrible way to name your arrays. So we're going to go with the example on the right. Let's just assume that is declared as degrees. If we want to access the first element at index 0, we would do degrees sub 0 and it will return 14. So now 1 degrees sub 1 returns 9, and so on and so forth. Now, time complexity is constant time access because you already have the index. It's not like you have to search and check and see if the element you're looking for matches the current element at hand, but that's what the next slide is about. So if you have an element that you're looking for, so you don't know the index and you need to confirm the existence of the element, all elements in the array need to be considered. Let's just say we're looking for 15. What we would do is we'll look at every element in the array. So on the right side here, I have another infographic here. And on this side, I'm showing you some of the variables or where they're at that current iteration and the result of the Boolean or the condition. But let's look at the pseudocode first. So pseudocode, remember, it's just as close to English as possible. It's not a specific programming language, but when you're creating pseudocode, what you should do when you're implementing solutions for the first time or trying to walk through a solution before implementing it, you should pseudocode first. So for search, what we'll do is we'll pass in the array as an argument and the desired element, which we know is 15. Right? First line of this function, we're going to do a for loop. We're going to look through the array from 0, so from 0 all the way to the length. And remember, what is length? Length is the number of used elements, and the number of used elements is 4. Okay, so 4, we're going to do from 0, 4 minus 1, from 0 to 3. So we're going to look through all of the elements from 0 to 3. So array sub I equal element, and if that current element matches what we're looking for, simply return the index. Otherwise, we'll just increment or increase the current index. And now that I look at the pseudocode right here, right, and which is the reason why you should create pseudocode, looks like I'm probably increasing the index twice. If we're being technical, because it say for I from 0 to array dot length minus 1. So it looks like it's incrementing here. So we could kind of cross this out here, but I kind of wanted to spell out that we're incrementing, but we could look at it like that, right? So sorry for that typo there. So you'll return -1 if the element is not found. Let's look at the right. Starting at the beginning, index is 0. Array sub 0 returns 14. 14 does not equal 15, so the condition is false. We're going to increment the index again. We're at 1. 9 does not equal 15, so that's array sub 1 gives us 9. So that's false. We're going to move forward and increment the index, or I keep saying index, but that's what I mean when I say I mean the index in this case. I is 2. Array sub 2 gives us 10. 10 does not equal 15, so that's false. Now I is incremented to 3. 15 does equal 15. The case is true. In this case, we're going to return the index. Let me cross that out again. So if we do search 15, we should get 3. Now let's talk about the worst case time complexity. So the worst case is the element you're looking for is at the very end of the array. So that means all n elements have to be considered. So the time complexity is n. Now let's talk about insertion, one of the operations I say you should pay attention to for dynamic arrays because it involves more tedious steps. So I have this covered. I just want you to look at the beginning and the result. So this is the original array here. And we're trying to insert 17 at index 2. Capacity is doubled. So a new array is created with twice the capacity and the element is inserted at that index, meaning that these two elements here are shifted 1 forward. Let's walk through the steps. So 1, the original array is at capacity. New array is created with twice the capacity. So we see this new array with all null values. We're not done here, right? Because now we have to copy the original elements from the original array. Everything in this array is copied over to this array. And that's what it looks like on 2. Now, 3, we need to update the reference. I did say you shouldn't use it as the name. It could be degrees, but I'm going to keep calling it array in this case because I'm doing terrible with naming it. So the array reference is pointing to the original. We have to update it to the new array. So you see that gets X'd out because we're updating the reference to point to the new array. We got the new array with twice the capacity, but we're not done yet because we need to shift the elements, 2 elements forward so we can insert this element in the middle of the array. If you see here, say length minus 1, and length again is the number of used elements, which is 4. So it's 4 minus 1, which is 3. So you see here, we have 3. So from 3 to index, 3 to 2, 3. So we can look at it going this way. From 3 to 2, the elements are copied 1 position forward of where they are. So 2 is going to be placed at 3. 3 is going to be placed at 4. And once that's done, you'll see we have a duplicate element here. We have 10 at index 2 and 10 at index 3. Now we're going to overwrite the element at index 2 with the new data because that's where we're supposed to replace it. So now you'll see with the blue highlight here that the element has been overwritten with 17. The worst case time complexity is O of n. When creating a new array, all n elements have to be copied, right? We had to create this new array. If you look from 1 to 2, we had to create an array with twice the capacity and move over the existing elements, all n elements. Okay, so I hope that provides clarity. Now let's talk about the pseudocode. We have the steps corresponding to the lines of code in the pseudocode. The insert function, you're going to pass in the array, the element, and the position. First thing you want to do is check if the position is valid. Because if someone is trying to insert an element at index 12 for this array, that's an invalid position. Or -1 or -2, anything that's less than 0. So if it's not within that range, we're going to return false because it's an invalid position. Next thing you want to do is check if the array is full at capacity. Resize if necessary. So if you do array.length or size, depending on the program language, if they use size, I'm not sure what program languages use size, but it's synonymous. If the array length is equal to the array capacity, we're going to create a new array with twice the capacity. Now I didn't define the pseudocode here. I just wanted to show this simplistically without showing the create array. But if that's something that you would like me to include to help you out, then please do let me know. And then the next function, you'll copy the elements. So copy the elements over from the original array. So you see array, new array. So cool. After you copy the elements over, you need to update the array reference. So on step 3, you see we're updating the reference here. So 4, we need to shift the elements to make space for the new element. So for I from array.length -1 to position, we're going to, for each element, we're going to update the next. So you see 2. Sorry if my handwriting is atrocious. Array sub 3 is going to equal array sub 2. And array sub 4 is going to equal to array sub 3. So that's how we shift the elements. And then lastly, we need to insert the element at the specified position, which is 2. So that gets overwritten. And last but not least, you need to update the array length by 1. And they return true because the insertion is complete. Now, deletion. We're going to talk about deleting an element at a specified index. And this is the original array. The original array is right here. So if we want to remove an element at index 3, that's 15. We don't want the null value in the middle. We need a shift so that it's at the end of the array. So you see here, the result shows that the null value shifted to the end. And 21 and 8 is over here. So now let's show the steps. So what we're going to do is set degrees sub 3 equal to null. So step 1 shows us setting degrees sub 3 to null, and now null is in the middle of the element is in the middle of the array. What we need to do, we need to shift elements to fill the gap. What I mean by shift to elements to the left, I'm talking about these elements to the right of that null value. We need to shift that to the left. So either that, it's the same as shifting this to the right. Now let's talk about worst case time complexity. So worst case time complexity is O of n, because deleting an element at the beginning of the array, if we say, for instance, we deleted 0, set this to null, right? Now we need to shift all of these elements to the left to fill the gap. And you just get rid of the constant. So that makes it O of n. Okay. Now here's the pseudocode. Pseudocode, same thing. You got to check if the position is valid, because if not, it's an invalid position. And it's much more simpler than insertion. You'll just set the element at that position to null. Now you'll shift the elements as well. Shift it to the left. So also, I forgot, let me call that out. You need to update the length of the array. So you need to subtract 1 because we did delete an element. So now let's talk about how data is stored. So I'm only going to talk about stack and heap of the memory layout. On the right side here, this is how the memory looks for a C program. And the heap grows downward. So this is a high address here, and it goes downward. So the address gets lower. And the heap grows upward. So we start at a low address and that grows upward. It'll make sense later. And the reason why I'm mentioning this is because of the address that will be shown later in the next slides. So how local data is stored on the stack. Stack memory is allocated when local variables are declared in a function. So here, this is a code block, a function, main function. Again, in pseudocode, we have 2 variables. We have C and X, C of type character and X of type integer. Now, memory is automatically deallocated once the function exits, right? But it's allocated when we enter the function. Memory size is determined at compile time and cannot be changed. And the data is stored in a LIFO fashion. Last in, first out. So we have C and X of different primitive types. So the character is a primitive type and integer is a primitive type. And it is static, meaning the size does not change. And also it's not dynamic. And it's defined in the main function. So it's stored on a stack. Character A is stored at address, we'll call this 2002, occupying 2 bytes. Now we're going to assume that characters take up 2 bytes and integers take up 4, right? On the right side, these are all, even though the boxes of the same size here, they take up different bytes. I just made it a little bit more simpler, but it probably confused you. If so, just let me know. I apologize and I'll do better. So this, when you see 0x, I mean hex address, and this is what it looks like here. So for 3000, this is what it looks like in hex. So you can just ignore this part here. It's not important there, but what's at 2002 is character C and the value is A. I don't know why I drew an A there, but it's sloppy anyway. And it's going to occupy 2 bytes. So we're going to move 2 bytes downward because remember, the stack grows downward. So now the next available address is 2000. And 27 will be stored at 2000, occupying 4 bytes. So int x 27. Here, if you pay attention to the legend, it'll show you the type, name, and value. Now, it's probably thinking crazy because it's like, wow, how did we get from 2000 to 1 FFC? So let me show you how to subtract hexadecimal here. 2000, we got 1 FF, F, and then 1 FF E, and then 1 FF, let me zoom in, 1 FF D, and now the next available address will be 1 FFC. If you're not aware with hexadecimal, it could go from 0 to E. So that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, right? So that's 10, 11, 12, 13, 14, 15, 16. So 16, that's hexadecimal. Now in decimal, if you're familiar with decimal, you know that goes from 1 to 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then for binary, it's just 0, 1. So this is hexadecimal. Goes from 0, I'll just say from 0 to E, 0 to F. Sorry about that. So hopefully that provides clarity on why the next available address will be 1 FFC, okay, because we're subtracting 4 bytes. So cool. That took up a lot of time. Let's talk about heap, and I'll hope to get through that much faster than the stack. So heap memory is allocated when dynamic memory is requested during runtime. So it's manually handled via allocation or deallocation functions. For C, some of the functions are called malloc and free. Malloc for allocating memory, and free for freeing up the memory or deallocating. Some programming languages offer automatic heap management, like Java's garbage collection. So if you code in C before, you will have some appreciation for Java. Now, dynamic arrays, assuming that degrees is a dynamic array declared because it's pseudocode. I'm not doing this in a specific programming language. It might look different in the syntax. So heap is going to allocate memory for the elements of degrees. So these are elements, right? So 8, 21, 15, 10, 9, and 14. So on the right here, you're going to see the heap. Remember, it grows upward. At the starting address of the heap, let's just assume that we have 10, 14, the first element. So degrees sub-0, 8, 21, 15, 10, 9, 14, the last element of degrees is in the heap. So the elements of degrees stored in heap. The reference to the first element is stored on a stack. 0, 2002. So degrees with the value 0x1014, the first element address, is stored at 0x2002, occupying 4 bytes, assuming that references take up 4 bytes. Now, we're going to assume that also integer take up 4 bytes. Again, it will vary depending on the programming language and your system. So remember here, I showed you that it's type, name, value. We have the character and then the value here. On here for dynamic memory, we have the name, and the value is a reference to the first element. So this will be 1014 stored here. I just have an arrow pointing here to make it look, I guess I'm trying to be fancy in that case. So what happens when you insert an element into an array that's at capacity? What will happen is that a new array will be declared on a heap with twice the capacity, and the reference will be updated, meaning that the pointer or reference to the first element will point it somewhere else, right? We have 6 elements here. So if this is at capacity, it's going to be updated to 12. So 12 elements will be allocated on the heap, and the stack will be updated to point to the first reference. Now, time complexity. Here I have worst case, average case, and best case. You should familiarize yourself with all of the cases just in case you get asked that in the interview question. My experience, I think I've dealt with worst case and best case, but just to be safe, familiarize yourself with all of them. So access is constant time because you have the index, right? Search time is all of n, worst case. Say, for instance, the element you're searching for is at the end of the array. And the average case is all of n. Best case is constant time, is where you're searching for the element at the beginning of the array. Now, insertion, and you see I have like 2 here because there's like a special scenario for insertion at the end of the array. So if you're doing insertion, the worst case with ON, you're inserting an element that's full or at capacity. You have to create a new element, new array with twice the capacity and copy over n elements to the new array. Now, average case is all of n. Best case is constant time, meaning that the array is not at capacity, and you're just simply inserting the element at that index. Also don't have to shift. So best case, you're inserting at the end. The next part, all of n, worst case, you're inserting at the end. You have to copy the elements over to a new array that's twice the capacity, and yeah, then you insert. So that's all of n. Average case for insertion at the end is all of 1, amortize. Think about it. When you're starting off with an array, just say it's empty and it has a capacity of 5. For the sake of my drawing, we're going to say 4. So we have an empty array. It's nothing in here. We could call it null. We're just going to assume that these values are null. It's nothing in the array. How many insertions you have to do for the array to be full? 4. So you have to insert an element here, 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 and here before it's at capacity. So when you do your 5th insertion, now you have to resize the array, and it's going to have an array size of 8. I'm just going to do that. 8, 4. And then you have to do not 8 insertions. You have to do 5 because now you did 4 plus 1. So it's going to be 5 elements in here, and you had to do the insertions there. But if you think about it, it's going to keep doubling in size. So it's going to go from 4, 8, 16, 32, 64, and there's more elements you have to keep inserting. So it's growing, it's doubling. When you do the average case analysis, it's all of 1 because it's growing much larger at a faster pace, meaning that the insertions that you have to do are going to be more constant time than all of n. Hope that provides more clarity. Now, best case again is all of 1. So now deletion, all of n, the worst case is because you're deleting an element at the beginning of the array and you have to shift all elements. Average case, all of n. Best case, all of 1. You're doing the deletion at the end of the array and there's no shifting required. At the end, all of 1. Worst case, because it's the end of the array. Same thing for average, same thing for best. Okay. Now let's jump into the code. I am taking up quite a time. I was hoping to get the video in a much shorter time, so I'll do better with presenting. But if there's any tips, please do drop a comment below, or suggestions, drop a comment below, or concerns, let me know. But subscribe, please do subscribe. So let's jump into the code, right? So I want to show you the C code first. If we look right here, we have a program in C for defining static array and dynamic arrays. So what I'm going to do here is I'm going to comment this out, and we're going to print. So this is the static array. This is the signature, how it looks in C. So this is how you define it. I have the size in this for loop right here. I am looping through each element of degrees, and I'm printing out the element here. So I have a little fancy print here to print out the index, the element, and the address. And you see is occupying 4 bytes. So you see 0, 4, 8, C. So remember I told you hexadecimal. Each digit goes from 0 to F. Hope that provides clarity. Now defining a dynamic array in C, you would do this signature here. So int star degrees equal malloc, and you'll do size times size of int, because you need to figure out how many bytes does an int take up, and it's 4. If you want to verify the size of an integer, you can do size of int %zu bytes, and then the size of int. So let's run that and see what we get. Size of int 4 bytes, so it takes up 4 bytes. So just for confirmation, I wanted to do that because when I hover over this in the IDE, I see unsigned long for UI 64, and 64 bits, I believe, is 8 bytes. So I can't make sense out of that, but just to verify, size of int is 4 bytes. We now are stepping into the realm of Java. We're going to do the same thing. We're going to define a static array and then define a dynamic array. When defining a static array, this is what the signature looks like. It is the type, open bracket, close bracket, the name, which we're going to, in this case, we're going to do degrees, equal. On the right side, it will be new, the type again, open bracket, close bracket, and then the curly brackets. And if you're defining the elements right then and there, you can set it up there. But if you're not, you can start it off with an empty array, but you have to provide the size. You have to provide a dimension. So if you do 8, the array has a size of 8. But in this case, I want to define the elements thereon, and we can actually print it out here. So for cool thing about the IDEs, it'll do that for you. So here I have integer I starting at 0, I less than degrees.length. And what we're going to do is we're going to do s out tab system.out.print new line degrees sub I. First we want to save it, then run it. We have hello world 8, 21, 15, and 10. Now let's do the same thing for dynamic arrays. So we're going to comment this out. Here we're going to use array list, which is a implementation of the list interface. And here we're using integer. You see it's with a capital I, and integer is a wrapper class for the primitive type. So you see this is lowercase, that's a primitive type. Here is a wrapper class. I just wanted to call that out. It's not really important for this case. I just want to show you a dynamic array. With this, you have access to functions like add or remove. So now you can just add the integers we want to include. So we do 1, 15, 10, and 21. Now you see right here is red because they're not primitive type, so you can't access length like that. So length is not resolved. How you get that is by doing dot size in Java. So array list, you can't use the brackets to access that. So you'll do degrees dot get, and then you'll pass an index. That should work. And see, that works. Another way will be, it's like a for each that iterates over an iterable. So list, array list is iterable. You can just do integer here. So that will work as well. 2 options. Boom, so that works. So I showed you C, I showed you Java, let me show you Python. So I don't think there's a way you could define a static array. There is a way you could define some dynamic array. They define this as a list. Here we can do degrees dot append, and that will append it to the end of the list. So append, remove, or insert. Insert the object before index. This is dynamic. Let me just print out the array, well, elements of the array. So let's do for element and degrees, or you could just do for degree. But it's easy to get tripped up because this is plural and this is singular. So that's just, we could just do element. I'll name it something shorter. So do print element. Right, let's see what that prints out. That will print out 8, 21, 15, and 10 in that case. I have now covered arrays across 3 different programming languages. I hope that provides some insight, and let's bring me back full screen. Obviously the animation isn't working. Boom, now the animation working. So that's going to take a little practice for me. If you stayed this long, I hope this provides some insight, and I hope to not take too long creating the slides for the next data structure. If you found this video helpful, please do give it a thumbs up and consider subscribing. Follow me on social media platforms at CodeHerc, or connected with me on LinkedIn at Byron Jenkins. If you have any questions, comments, or concerns, feel free to drop them under the video or reach out to me directly. Whatever works for you. Take care.